Now let's take a look at the 25 milliliter graduated cylinder. You'll see again that we are going from here to here, which is actually just a difference of 5 milliliters this time. And that 5 milliliters is broken up into 10 increments, giving us just 0.5 milliliters per increment. So if we want to calculate our uncertainty, we would take this number here, this 0.5 milliliters, our smallest increment, and divide that by 2 because we're taking half of it. And so that gives us our uncertainty over here of plus or minus 0.25 milliliters. So when I want to measure this time, I'm going to again count my lines. So that I'm going to get 10.5, 11, 11.5, 12, 12.5, 13, and we're somewhere close to this 13.5 mark. So we're going to take a look a little bit closer. Since we don't see that it's right in the middle of those marks, I probably wouldn't call it 13.25, but what we can call it then is 13.50 milliliters. This 0 is important because we have our uncertainty goes 25, 50, 75, and 100. So it would be 0. This 0 is significant. It's important because that's how well we can know that number. Now, because of this, we can see that this is a more precise tool. And the reason why we say that is because these 4 digits here are greater than the 3 digits of what we obtained over on this side. So the more digits you have, the more precise your tool is. Oh, let me bring that up just a little bit. We're going to go ahead and look at this ruler now. So we have this nail, and we're just going to take any object and we're going to use it as a straight edge so that we make sure that we're getting our edge right where it needs to be. So we're going to take this, we're going to drop it right down to the ruler so you can see where that ends. So we are looking at a centimeter ruler, okay, and here we have 1 centimeter, and if we count up the spaces that are in between it, we will get 10 increments. So we know that every line is equal to 1/10 of a centimeter. So here we go. We're going to find out this is 1 centimeter, and then we're going to add the tenths. 1, 2, 3, 4, 5, 6. But it's not quite all the way to that 7th one. So now we're going to find out how certain can we be about this number. So we can say 0.1 centimeters. Again, we're using this number because it's the smallest increment, divided by 2. And that's going to give us plus or minus 0.05 centimeters. So I might say I don't know this number quite well enough to get to 1.70. I might say that it's 1.65 centimeters. And this number is not going to change. So all of these lead us to significant figures. Sig figs are a shortcut to communicate about that uncertainty developed from studying the plus or minus values in measurement and calculations. More sig figs mean a more precise measurement. So if, again, we looked up here, there's more, we call these 4 digits significant figures. That means this test tube was more precise. This meter stick right here is only precise enough to give us 3 significant figures. And significant figures become important because you can change around your units, but you have to maintain the same significant figures. So for instance, if we say this was in centimeters up here, so we have 1.65 centimeters according to that. We have 1, 2, 3 significant figures because that was all that we could measure. So we're going to say 3 sig figs. Now if we want to make it bigger, we're going to move the decimal point over this way, and we're going to get 0.165 decimeters. Excuse me, yeah, decimeters. So we're still looking at 1, 2, 3. We still only know this accurately to 3 numbers. This 0 there is just a placeholder, so we still end up with 3 significant figures. Again, we're going to move it. We're going to get to meters, so we're going to look at 0.0170 meters, or excuse me, 165 meters. Again, these zeros are only acting as placeholders. We're moving around the same numbers. We're just putting in zeros where the decimal needs them to go, so we still end up with 3 significant figures. And if we're converting it all the way to kilometers, we're going to jump a couple zeros in here. We're going to end up with 0.0000165 kilometers. We still end up with 1, 2, 3 numbers that we measured up at the top here. And so we're going to say that still, even though we have all those zeros in there, there's only 3 numbers that we've actually measured, so we're only having 3 significant figures. Okay, now we're going to go back down. So this time we're going to go from centimeters to millimeters, so we're going to move the decimal in the opposite direction. So we're going to get 16.5 millimeters. And notice we still have 1, 2, 3 numbers that we measured, so we here, and we're going to move it down to micrometers. So the important thing here, even though this is a big jump, so we're going to go to 16,500 micrometers. Even though we have all of these zeros here, they are not significant because we didn't measure them. We only measured these 3 digits. So again, we end up with 3 significant figures. First of all, any numbers that are not 0 are always significant. So that 1, 6, and 5, those are always significant. So if I come up with a measurement of 72.3 grams, every single one of those numbers would be significant. The second rule is that any zeros between 2 non-zero numbers are always significant. So say I have 6,001 grams. Those zeros are necessary to show where that is. If they're not significant, then I end up with 61 grams, and that we can't have. Number 3 says final zeros are significant only if the number contains a decimal point or the 0 has a bar over or under it. Now this is really important to remember because this is where it gets tricky. For instance, if we're looking at 4.30 kilometers, this 0 becomes significant because if it wasn't significant, we wouldn't have to write it. All we would have to write is 4.3. The 0 might also have a bar over it. So say I'm talking about 430 kilometers. This would only be significant if I put a 0 over it, or excuse me, a line over it, because otherwise it's a placeholder and we don't know how accurate that is. Number 4 says leading zeros at the beginning of the measures are never significant. So for instance, if I have 0.002 seconds, then I'm just going to write that as 2 times 10 to the negative third seconds. Because these leading zeros, they just tell me about the size of this number. They don't actually tell me about how accurate or precise it is. So we're just going to leave that 2 like that. Finally, if you ever run into any kind of counting number or defined constants, they always have infinite sig figs. So if we say that we have 6 people in the room, it has to have infinite significant figures because 6 people is all we can count. We can't count 0.2 of a person, so we have to have infinite sig figs assumed on this number. All right, that's it for now. Have a wonderful weekend.